Welcome to 6034 Office Hours, Fall 2020 edition. So this is much like the other Office Hours video that I recorded. This is a supplement to the recitation video and to the material presented in 6034. Particularly, these are going to be related to neural networks. So in this session of Office Hours, I'm going to be showing you how the chain rule in calculus leads to the equations that I presented in the neural networks video on backpropagation. So the reason and the motivation behind this video is in the recitation video, due to this material being, or the calculus heavy portion of this material being outside of the scope of what we would require of our students in 6034, I presented the equations and I said these equations come from the derivative of the mean squared error in the context of the recitation, and that's more or less how you do it, and these are the equations. So I wanted to give some background to the equations on where they come from, as I mentioned, and they also present a different way to arrive to the same equations. And I believe it leads to a much more well-grounded knowledge of or understanding of neural networks when this is also understood. So to just jump right into it, I'm going to start with a basic network. I only have one input node, one hidden layer, or one node in the hidden layer, then one output node. And I'm going to be performing the chain rule to get the weight update equation for W1, and then I'm going to show you how it's the same as the equations that I presented in the recitation. So, but first, a reminder that of the mean squared error. I addressed this in the recitation video, but I'll say it again, that mean squared error, as the name mean implies, it's the error across all the training points, but here we're only considering one training point, so we could say it's the squared error. But because the name is mean squared error, it's generally used that way, I keep the MSE notation, and I refer to it as mean squared error. And we want it to be as close to 0 as possible, which is indicative of our neural network committing fewer errors on the points that we give it. And then in order to use the mean squared error, we compute the gradient of it with respect to the weights of the neural network, and then that gradient then is the slope, or basically the direction in which we need to move the weights for us to improve performance of the neural network. And then finally, we know the direction with the gradient. We need to then know how far to go in that direction, and that's what the step size is, which is typically either given to us or we find it via multiple rounds of training and optimization. So it's a more empirical finding, the learning rate, or R, rate constant. Okay, so let's jump right into it. So I'm going to rewrite the mean squared error here. This is going to be out star, and in this case, out B, because out B is the output of the network. This is going to be equal to -1/2 out star minus out B squared. And if I want to calculate in which direction I want to change W2, weight 2, I need to calculate the partial derivative of the mean squared error with respect to the partial derivative of W2. Using the chain rule, I know this is equal to the derivative of the mean squared error with respect to the output of the network. Then I can multiply this by the partial derivative of the output of the network, or the output of node B, with respect to the input to node B. So this is going to observe more or less the rate of change in the node from between the input to the node and the output of the node. So this is going to basically focus on the effect of the threshold function in the final output. So in a way, it's the derivative of the threshold function. Then I need to calculate the derivative of the input to the node B with respect to weight 2. Okay? We can eyeball this one, the derivative of the mean squared error with respect to node B, because we merely have to take the derivative of this equation right above it. So this we know to be out star minus out B. Then we take the derivative of the sigmoid function, and you can look this up yourselves. The derivative of the sigmoid function, which is the threshold function that we're using. Let's say that, as a side note, this is the derivative of the sigmoid function. It's equal to the sigmoid function times 1 minus itself. And the sigmoid function would be, in this case, sigmoid of NB times 1 minus the sigmoid of NB to adhere to the NB with respect to NB notation. And we know this is merely out B, and this is also out B, so I'll rewrite it below. And then finally, the derivative of NB with respect to W2, NB is equal to W2 times out A, which means we only have out A here. So finally, this ends up being out star minus out B times 1 minus out B, and then finally out A. Let me erase this shortly. And now let's go and look at the equations. I dropped something earlier. Oops. Let's go look at the equations that are presented in Recitation. So we see, taking a look at this, that it does correspond to fairly well to this equation, because the node B is in the output layer. We have out B from the derivative of the sigmoid. We have 1 minus out B from the derivative of the sigmoid. This is the derivative of the mean squared error. And then at the very end of the equation in the canvas, right here, out A, this is this out A. And then we don't have the R term because I calculated only the gradient, the direction in which we would go. Then I multiplied by R, and that would give me delta WAB, as in the document that I'm presenting here on screen. So we know this method works this way. So that's fairly simple. I want to give you a more challenging example for you to see where this sum comes from. This sum of WBC delta C. Okay, so let me squeeze this to the corner. And what I'm going to do is I'm going to calculate the weight update equation for W1. And you'll notice I'm going to need the following paths. This one and this one. And you'll see what I mean as soon as I start with the weight update equation. Okay, so the partial derivative of the mean squared error with respect to W1. I'm going to take it a little bit more slowly because the chain rule is a notational nightmare. It has a lot of notation involved and a lot of roundabout calculations, so it's very easily, I could easily commit a typo or mix up. I recommend if you try it at home, make sure you verify and double check everything. Okay, so this is derivative of the mean squared error with respect to the output of the network, which is, sorry that I'm so close to the mic, out E. With respect to out E. Then this is a partial derivative of out E with respect to in E. And now this is the partial derivative of in E with respect to out C. Yes. And then this is the partial derivative of out C with respect to in C. Notice I'm going, notice the pattern. I'm going output to input to output to input to output. But notice that I want you to notice, and this is where one of the reasons why I wanted to take it nice and slow. The mean squared error is the rate of, when I calculate the mean squared error with respect to a particular weight, it's the rate of change between the error and that variable. So when I change this weight, how does the error change as a function of everything that came after that weight? So I know I not only need to take into consideration the weight and the error, I need to take into consideration everything that connected to that weight after the weight after I change the weight, because everything else is going to change. So in reality, I've made a slight mistake at this point, because let me back up a little bit. This is going to be the partial derivative of NE with respect to W7, or W1, sorry. Our interest is W1. And I think this will make it a little bit clearer on why W1. So let's start by writing the terms out, and then I'll continue the derivation. So this is going to be out star minus out E. Out E with respect to NE, that's the derivative of the threshold function, which is the sigmoid, as I mentioned earlier. So this is out E, 1 minus out E, And then I need to take the derivative with respect to w1 of the following function. In E, which translates to out C times w7 plus out D times w8. And this is where the chain rule gets very, very messy. Because now I have my chain rule has branched effectively. But notice that that is what happens here. When my neuron, when the weight for which I want to calculate the derivative of with respect to the mean squared error, or the other way around. When I want to calculate the derivative of the mean squared error with respect to a weight that is not in the final output layer, then I need to sum over the later connections. So we're seeing it again, but in reverse. So we're seeing the split. And now that you've seen that, I'm going to make the board big again so that it's easier to read. So this is out star minus out E. Actually, I'm going to abbreviate this to make it even easier. I'm going to call this chunk. I'll go briefly back to the PDF. I'm going to call this chunk at the very beginning delta E, so that I don't have to write absolutely everything. This is delta E times the partial derivative of out C times, with respect to w1 times w7 plus the partial derivative of out D with respect to w1 times w8. Delta E, and then this in turn turns into the partial derivative of out C with respect to the partial derivative of in C times the partial derivative of, well, I'm going to move this w7 to the beginning so that it doesn't get lost. So this is going to be w7, then all the partials in C with respect to w3. Whoops. In C with respect to out A. Apologies. It's in, out, in, out. Then the partial derivative of out A with respect to the partial derivative of in A, and then the partial derivative of in A with respect to w7, the partial. Okay, so that's 1/2 plus w8 and then a bunch of partials. I'm going to leave it as out D delta of w1, or partial of w1. I'm going to leave it like that until we solve what the heck is going on with the first half. So allow me to duplicate the slide. so that I don't lose that bit of information. I'm going to erase the top here. Let me move this. Okay. Out C with respect to in C. This, I've mentioned it a couple times already. This is the derivative of the threshold function, which is a sigmoid. So this is, let me drop the red. Out C, 1 minus out C. This is in with respect to out A. This is W3 because in, oh, I'm missing a letter there. In C. In C. In C with respect to out A. In C is equal to out A times W3, so this is just out A. Or this is, sorry, this is just W3. And then out A with respect to, well, before going there, let's take a look again at the equation. So this is out C, 1 minus out C, and I'm looking at the PDF right now. And then I have W3 here, and I am about to go even further back with this out A versus in A by doing out A, 1 minus out A. So this is consistent with our chain rule so far. Because in looking forward, we're going from, if we were using these equations, we would be going from W1. So we would be interested in delta A. Delta A would be out A, 1 minus out A, times the weight that connects the neuron A to the next neuron, which is, in this case, W3, correct? Yes, W3. And then delta of the neuron that goes next, which is delta C, out C, 1 minus out C, and everything that comes after. So far, this is more or less delta A. Well, I say more or less, this is delta A in the sense expressed in these equations. So we are correct so far. And then finally, we have in A, the partial derivative of in A with respect to W7, which is in A is just W7, or not W7, W1. Sorry about that. W1, and that is just X. So let's take a look one more time. I don't have my rate constant or the learning rate because I'm only interested in the direction, the step size, out A. In this case, this is X. This is X. And then I have to multiply it by delta, the delta of the next function. In the PDF it's B, but in my whiteboard it's A. And that delta translates to out A, 1 minus out A, times the following weight. We're good there. The delta out C, 1 minus out C, and then the rest which would be delta E. Which is consistent so far. So this, let's see. The only thing that we're missing now is the sum, because recall that this is a sum, and the outgoing connection here, there's the weight W3 going to node C, but then there's also W4 going to node D, and that we're going to get from over here. Oh, I dropped. Well, I haven't dropped it. Let me formalize this. This is then equal to delta E Okay, so the reason I've been staring at it so long is if you're not seeing the connection between the delta C, the delta C here, and how delta E is going to come into play later, remember that when we go to calculate delta E, we're also going to get the 1 minus out C, then we're going to have to multiply by the weight connecting node C to node D, or node E, sorry, which is W7, which is right here. I hadn't rewritten it. And then we're going to get W7 times delta E. So we're perfectly on track. And I'm going to bracket it a little bit so that it's easier to see. No pun intended. Let's see, I'm looking for a convenient way to bracket it. So this would be W7 out C, 1 minus out C. We can say that this is more or less delta C. I say more or less because delta C includes delta E in its terms, but I'm going to leave it as delta E here. Or delta C, sorry, delta C approximately, so that you can see all the deltas side by side. And then we have W3 out A, 1 minus out A times X. And this is, I'm going to say, approximately delta A. And again, approximately, because delta A includes delta C in its calculation and delta E, I'm choosing to just cut it off and say this part is delta A, just so that, again, you can see delta A, delta C, delta E. And as a quick reminder, this is a larger parenthesis because we had a sum when we were calculating delta, what was it? When we were calculating in B earlier, so we still have to deal with this sum over here. Plus this sum. Let me rewrite this on the following page by copying this one. is going to be equal to delta E. So the other caution I would say is, because we're going from back to front versus front to back, the summations, they would group differently. So you may ask about going from B to C. That's in our case A and C, I believe, and then to E. So because we're going backward, the summations are appearing in different order, and they're grouped a little bit differently, but as we're seeing so far, we're arriving to the same solution. So this is delta E, delta C, the way I've defined it, times delta A plus, times X. Times X plus W8. And now I'm going to expand. Expand what I was doing with out D and W1. I wonder why it doesn't want to move. There we go. So this is the partial of out D, D not B, with respect to in D. Then this is the partial of in D with respect to out A. Oops, I missed the partial there. Out A. Then I need the partial of out A with respect to in A. And then again, the partial of in A with respect to W1. And so this turns into X again. Let's see. What did I drop a term accidentally? No, then I'm going to get out A in A, or out A with respect to in A. This is going to be, again, the derivative of the sigmoid function. This out A in D with respect to out A. This is W4. Oh, yes. So the problem was, I'm going to rewrite this a little bit. There. I'm not going to include W3 because it's going to change. So this is, I really butchered a few things there that I shouldn't have butchered, because this should not include W7. Be careful, be very careful. You're seeing firsthand, you're witnessing firsthand the notational nightmare that it is to perform the chain rule by hand. So I'm gonna quickly correct this. This is W7 delta C, sorry. Delta C. W3 delta A times X. There you have the weights explicitly. Then I have again here delta A. And then to continue, in D versus in D with respect to out A, that's W4. I have it right here. And then out D with respect to in D. That's the derivative of the sigmoid, 1 minus out D. Okay, and I'm going to use this notation again. And what I end up with at the very end is delta E W7 delta C W3 delta A times X, but I'm going to factor X out. Plus W8 delta D W4 delta A and X factored out. And I can more or less move the terms around such that it fits in with the PDF that I have here. By the way, I forgot to change it back to the large whiteboard. Apologies. I'll just leave it up because now we're more concerned about how it lines up with the PDF. So I'm going to move this around and say this is X times delta A, which is the first term that comes, or the first node that comes after the A is the first node that comes after X, delta A, and then this is going to be let's see, W3 times delta C, and this then turns into W7 times delta E plus W4 times delta D, and then that turns yet again into W8 times delta E. So this is, it's not exactly one-to-one in terms of how the terms are defined because of how I had to more or less group them so that they would all fit on the canvas page, on the, not the canvas page, the canvas basically. But this is, let me just make it a little bit bigger shortly. But this was meant to be it's not a preview, not a preview, is, well, as I said in the beginning, where do these equations in the PDF come from? And this is actually where they come from. The equations that I gave are meant to just simplify a lot of the calculation so that you're not thinking to yourself, oh, is it this one with this one with this one, which partial derivative am I on? So the equations were meant to simplify a lot of those mathematics. Unfortunately, they're strictly, as they strictly tied to sigmoid threshold functions and other assumptions. But this is the origin of those equations, and this is the chain rule as used to train deep neural networks in gradient descent in general. So if you're able to understand the chain rule, the way it's used here, you have an extremely good understanding, or you will have an extremely good understanding of neural networks and gradient descent and how to train them. And with that, I'll be signing off, and I'll see you on the next one. I hope that this small, rough around the edges office hours were helpful, at least to your mathematical intuition and to your understanding of neural networks as a whole.